In the last class, I introduced you to calculus and then we looked at velocity a little more closely. Now, when a particle's velocity changes, the particle is said to undergo acceleration. For motion along an axis, the average acceleration, that is A average, over a time interval delta t is defined as the change in velocity divided by the change in time. That is, A average equal to delta v by delta t, and that would be equal to v2 minus v1 divided by t2 minus t1. Now here the particle has velocity v1 at time t1 and it has the velocity v2 at time t2. Note that v1 and v2 are instantaneous velocities. Now, just like we discussed average velocity and instantaneous velocity in the last two sessions, we can also talk about average acceleration and instantaneous acceleration. Instantaneous acceleration is the acceleration of a particle at any instant. That is, the rate at which its velocity is changing at that instant with respect to time. Just like velocity at any point is the slope of the position-time curve at that point, graphically, the acceleration at any point is the slope of the velocity-time curve at that point. From our last class, we know that the slope of tangent to the curve at a particular point is equal to the derivative of the curve at that point. Therefore, we can write acceleration as A equal to the derivative of velocity, that is dv by dt. Since velocity is derivative of position, we can further write that as d by dt of dx by dt, which is basically the derivative of a derivative, and we call it a second derivative. So acceleration is basically a second derivative of position with respect to time. This can be read as A equal to d2x by dt square. Now let me repeat. The acceleration of a particle at any instant is the second derivative of its position x with respect to time. Here, as always, we have assumed that x is a function of time. A common unit of acceleration is meter per second or meter per second square. Other units are in the form of length upon time by time or length per time square. Acceleration is yet another vector quantity and has both magnitude and direction. Its algebraic sign represents its direction on an axis just as for displacement and velocity. That is, a positive acceleration means that velocity is increasing in the positive direction of the coordinate axis considered, and negative acceleration means that velocity is decreasing along the positive direction of the coordinate axis. If acceleration is constant, the average acceleration and instantaneous acceleration would be equal because, well, the acceleration then would have the same value at any instant during the motion of the object. Let's say that value of acceleration is a with an appropriate unit like meter per second square. Let's also say that the velocity is v0 at time t equal to 0 and v at a certain later time t. So a equal to dv by dt. And from that we can say that dv equal to a dt. If we integrate both the sides of this equation over the time interval 0 to t, we can derive as shown that v is equal to v0 plus at. Now we can integrate that once more. Let's see where that takes us. Let's say that the position of the object at t equal to 0 was at x0 and at a later time t it is at x. If we write v as dx by dt and perform our integration once more over the time interval t equal to 0 to a later time t, we can derive as shown that x minus x0 equals v0t plus half at square. So we've got here the two basic equations of motion with constant acceleration. The first one is v equal to v0 plus at, and the second one is x minus x0 equal to v0t plus half at square. These equations can be used to solve most constant acceleration problems. If we eliminate t from both these equations, we get another equation that's also pretty useful in solving problems. And that is v square equal to v0 square plus 2a multiplied by x minus x0. Now let's look at a special case of constant acceleration. We all know that if we drop something, it falls down. It doesn't take a Newton to figure that out, does it? If you tossed an object either up or down and could somehow eliminate the effects of air on its flight, you would find that the object accelerates downward at a certain constant rate. That rate is called the free fall acceleration, and its magnitude is represented by g. This acceleration is independent of the object's characteristics such as mass, density, or shape. It is the same for all objects. The value of g varies slightly with latitude and with elevation from the surface of the Earth. At sea level in Earth's mid-latitudes, the value of g is 9.8 meter per second square or 32 feet per second square. Generally, for simple problems of free fall near the surface of the Earth, we can assume g to be this constant value for all practical purposes. The equations of motion that we derived for constant acceleration also apply to free fall near Earth's surface, where we assumed that the acceleration is pretty much a constant. That is, they apply to an object in vertical flight either up or down when the effects of the air can be neglected. However, for free fall, which obviously happens vertically, please note the following. The directions of motion can be considered along a vertical y-axis instead of the x-axis which we normally do, with the positive direction of y upward. That's how we define y-axis in rectangular coordinate system. And it is more convenient choice of axis since the motion is vertical. The free fall acceleration is negative, that is, downward on the y-axis as things fall down with increasing speed towards the Earth's surface. And so, it has the value minus g in the equations. So, in the equations of motion, we can replace x with y and a with minus g. So, dear boys and girls, I hope you got a good understanding of the concept of acceleration. I would suggest that you pick a good textbook and start solving problems. And let me know wherever you get stuck. I will help you out or we'll figure it out together. My favorite book to learn and practice physics is Fundamentals of Physics by Resnick and Halliday. Another very good and extremely popular book is Concepts of Physics by H.C. Verma, which comes in 2 parts. And a great book to practice complex problems in physics is Problems in General Physics by I.E. Irodov. Get them and get going. Thank you and have a great time learning physics.